Ramanujan for G is now available on the Google Play Store. Try it out for free.
All right, students. So we're going to continue with rotation, and so today the topic is again going to be, we're going to look at torque, and we're going to look at angular momentum, and then we will introduce the idea of the moment of inertia. So, as I explained before, the angular velocity is a vector, and it is the time rate of change of angular position of a rotating body. So, in terms of the notation for the direction, if something is, let's say, spinning like this, like a top, right? It has an axis like that, and it is spinning about this axis of rotation, it is spinning like this, then the angular velocity is like that. If it is spinning like this, let's say it is a merry-go-round spinning like this, the angular velocity is in the toward upwards, right? So if it is spinning like this, right hand rule, it will be upwards. Okay, so that is the direction of the vector angular velocity. And so now, corresponding to that, you have this idea of the instantaneous angular velocity, which is again upwards. And if an object is moving around like this, it is if it is spinning like this, its omega is like this and the r is like this. So omega cross r, and therefore v is tangential to the path as expected, right? So uniform circular motion, the acceleration is tangential, the velocity is tangential, the acceleration is radial, right? So v is equal to omega cross r, and we already discussed that, right? Now we are going to discuss the case when something goes faster and faster and faster and faster, right? It starts rotating faster and faster and faster and faster. Its omega, which is upwards, is increasing at a continuous rate, right? If it's spinning faster and faster and faster, its angular velocity is increasing at an increasing rate, and therefore we say that it is experiencing angular acceleration, right? Now, the direction of the angular velocity is constant, but the magnitude is continuously increasing. Therefore, the angular direction of the angular acceleration is also along the direction of the angular velocity, right? So that this is the angular acceleration, right? Now, the acceleration itself, as you know, is composed of two components, right? When it was experiencing uniform circular motion, it had just a radial component AR, which was towards the center of the circle around which it was spinning, right? Now, in addition to that, it is also going to have an AT when it has angular acceleration, okay? And therefore, the AT is related to the angular acceleration using the equation alpha cross r. As you know, alpha is this way in the same direction as omega, because the direction of omega does not change, but its magnitude is increasing. Therefore, it is also in the same direction, right? Remember, d omega by dt is alpha. Omega is increasing in magnitude. Therefore, alpha is also the same direction, right? So now alpha cross r will again give you, just like omega cross r gave you v, right? Tangential. Alpha cross r will also give you tangential acceleration. Omega cross r gave you velocity, right? Like that, alpha cross r gives you tangential acceleration. So now the new acceleration has two components, a tangential component and a radial component, right? So the net acceleration is the square root of at square plus ar square, and it is the resultant of a tangential and a radial acceleration. All right. So now today I'm going to introduce to you this idea of precession. What is precession? Precession is what happens to a top. Let's say you spin the top and then it starts to spin and then you tap it slightly. If you tap it, what happens is there is a displacement of the top, and it is what your tap does do, right? Previously, the two forces acting on it, the normal force, right? When a top is spinning, there's the weight which acts downwards, and the normal force from the point of contact which completely repels it, right? Now, when you tap it slightly, those two forces will still be in balance. Okay, the weight mg and n are going to be like this. Okay, but they are now parallel, opposite in direction, but slightly displaced. This displacement is what causes this thing called torque. Okay, torque is the moment of a force. Okay, now what does this moment of a force do? Right, it makes the body axis spin. Okay, now this is the top spinning, right, is the same in some ways. It can be considered, this is called precession, right? The top spinning can be considered to be similar to uniform circular motion, right? What is happening, I will tell you what is happening later. Okay, but remember that now the omega is no longer like this, right? When it was when something was going in a merry-go-round, the omega was like this. When the top was spinning, standing vertically and spinning, the omega was like that, right? Now the omega itself is spinning. Okay, now the omega itself is spinning, right? And at each moment, right, the what causes this omega to change direction, right? So what causes the omega to change direction is the torque, and we will explain the value of that. Okay, still remember, what is that free body diagram and force balance etc. still works. Okay, it is only that now you have this added term. So rigid body dynamics, again remember the three equations, right? So now we're going to introduce this idea called angular momentum. The angular momentum is the moment of the momentum. The moment of something is merely r cross that something. So if there is a position with respect to an axis, okay, so if you have an axis, the r cross the momentum, r cross p, will give you angular momentum. Okay, so the angular momentum is also a vector. It is the cross product of two vectors, the position vector and the regular momentum. The moment of the momentum is the angular momentum. Okay, similarly, the moment of the force is called torque. Okay, now L is equal to r cross p. If you differentiate both sides, dl by dt equals dr by dt cross p plus r cross dp by dt. Now remember that dr by dt is v and v cross v is 0. Therefore, the first term goes to 0. So you just have r cross dp by dt, right? And r cross dp by dt we have met, right? What is dp by dt? dp by dt is f. According to Newton's second law, rate of change of momentum is proportional to the impressed force. Therefore, dp by dt is f. Therefore, dl by dt is equal to r cross f. So the moment, what is dl by dt? It is the rate of change of angular momentum. The rate of change of angular momentum is proportional to the impressed torque. It is the rotational equivalent of Newton's second law. And when we talk, what is the torque? R cross F. It is the moment of the force. Okay. Angular momentum is the moment of the momentum. Torque is the moment of the force. The rate of change of angular momentum is directly proportional to the impressed torque. So when we go back to the spinning top, what is happening is that the angular momentum L spins around. Angular momentum is, how is it related to the angular velocity? Right? How is velocity related to the linear momentum? Velocity is just the mass times velocity, linear momentum. Similarly, we will be introducing this term called moment of inertia. Right? Mass in some ways represents inertia, right? Like that, the moment of inertia, times the angular velocity gives you the angular momentum, right? So now, so L is I times omega, and omega is like that, and you can think of I. I is usually considered to be a tensor, but let's for now call it a scalar. Okay, therefore, if that is the axis, you have the or if it's something spinning like that in that axis, and the omega is like that, then correspondingly L is also along omega. Okay, I omega. All right. So now, having understood this, dl by dt is equal to tau, right? Sigma tau will give you dl by dt. Okay. So now, what effectively happens is that if there are inside a system of bodies which are having forces acting on each other, the torque due to some of these forces, like A applies a force on action reaction forces, will cancel out, and therefore it is only the external torque which leads to the change in the angular momentum. Okay, so dl by dt equals tau external. Okay, you can get a lot of questions that deal with this also, and it is good to learn this material, particularly if you're going to be taking the JEE, but also if you're going to be taking the NEET exam. The now the torque equation is analogous to Newton's second law, that is dl by dt. So now, what we are so now when you have problems dealing with mechanical equilibrium, we said sigma fi equals 0, right? The net force is equal to 0, right? For instance, we solve problems with pulleys, we solve problems with inclined planes. All those problems, we had the net external force being 0. Now we are going to add to that set of equations of the next external force being 0, which is caused when there is translation equilibrium, also the rotational equilibrium equations, which is that the net torque is 0. Okay, so the translation equilibrium gave us net force is 0, rotational equilibrium is going to give us net torque is 0, and therefore dl by dt is 0 when something is in equilibrium. Something is of course spinning, it's different. Okay, so now, we looked at this question, I think, yes, last time. Particle is confined to rotate in a circular path with decreasing linear speed. What can be said, right? Now, if it is rotating in a circular path with decreasing linear speed, you can say that the angular momentum is r cross mv, right? And how can angular momentum be conserved, right? Now, the direction of the angular momentum is conserved, right? If it's spinning like this and is slowing down, right, the omega stays that way, right? It spirals towards the center. may not spiral towards the center. Its acceleration is towards the center. No, its acceleration will have two components because it is also has a alpha t component, right? So it has the acceleration has two components, so its acceleration is towards the center is false. Only the direction of L is conserved. Okay, so this is a very good question. It asks you all the material that you learned so far, but it is a very simple question. Okay, it is the kind of question that you can expect in many exams because they want to know that you have learned the material and understood the material in great detail and therefore are capable of being accurate in understanding this kind of probing analytical questions about the material learned. Okay, so tau x equals 0 implies that dl by dt equals 0, which means that there is L is a constant. If tau ext is equal to 0, dl by dt is a constant, means L is a constant. Just like if there is no external force, momentum is conserved insofar as it does not, right? So this is the um, equivalent of Newton's first law. Law of conservation of angular momentum states that when there is no external torque on an object, no change of angular momentum will occur, right? So let's say the top is spinning like this, right? And it's continuously spinning like this about this axis. It is supposed to continue spinning like that forever. Just like if something was moving in with constant velocity, it is supposed to move with constant velocity forever, right? It's supposed to be inertial forever. Okay, so remember that. Now when a particle is moving with constant velocity, what happens to the angular momentum? Angular momentum is also constant because the r cross mv, the r keeps, although it is keeps moving about, so r is about an axis, right? So the r keeps changing, right? So now you must be saying, r is changing, mv is constant, r cross mv is therefore changing. No, r is changing, but r cross mv is constant. Okay, because r sine theta is a constant. Okay, mv is a constant and r sine theta is also a constant. R sine theta is merely the height. Okay, om by r equals sine theta. Okay, so because of that, r cross mv stays constant even when when a particle is moving in constant velocity. Okay, now let's look at this. Bob of mass m attached to an inextensible string of length is suspended from a vertical support. Bob of mass m attached to an inextensible string of length L is suspended from vertical support. The bob rotates in a horizontal circle, okay, with an angular omega about the vertical. Okay, angular, now about the point of suspension, angular momentum changes in direction but not in magnitude. Angular momentum changes in both direction and magnitude. Okay, now angular momentum is conserved. Okay, so now with a angular speed omega about the vertical about the point of suspension, right? Now in this case we ask about r cross mv, where v is omega cross r, right? So r cross mv, right? So the angular momentum in this case stays, actually I think this is not right. Okay. So now the dynamics of a rigid body. Okay, the force acting on a rigid body are of two types. Okay, the external forces and the internal forces. The just like the external forces alone cause um, the rate of change of momentum, right? Similarly, and the internal forces don't contribute to it. Similarly, the external forces alone affect the torque. So tau is r cross uh, uh, f ext, sigma r cross f ext. So moment of the force is what we call as torque. Okay, so now tau we already said is the rate of change of angular momentum. Okay, now we call two forces which act, which are opposite and perpendicular to each other as a couple. Okay, like so now if you had a let's say there was a propeller, about an axis, then I tap the propeller with two forces like this, right? Then it will start to rotate, right? Now that two forces that tap on both sides of the propeller, right, that is called a couple. When there are two equal and opposite forces that act counter to each other, it is called a couple. Okay, now in electricity and magnetism, we introduced this term called a dipole moment. Okay, so similarly, this is called a couple moment. Okay, now what is important is the moment of a couple is constant irrespective of the choice of the origin, right? Normally, if you wanted to calculate r cross f, right, you evaluate it about a axis, and the r can change with the axis, right? But for a couple, that is not true, right? And most often, when you deal with net force being constant, right, you will be dealing with couples, and the moment of a couple is independent of the origin. So in this case, there are two forces acting on A and B, r cross f for this one, r cross f for that one, right? Right? R cross f for that one, right? R cross f for this one. The when you add sum the two, you end up with r2 minus r1 cross f. So your position doesn't matter. It is only the this vector AB, right, which matters. AB cross F is the net moment of the couple. Okay, so remember that AB cross F. Okay, so now let's say you had a lever, right? The lever is based on this principle of moments. Okay, lever is when there are like when you are on that seesaw, right? When you're on a seesaw, this way it will go up, that way it will go up, etc. Right? So now, how does the seesaw move? I push my feet, right? When I go to the ground, I push my feet. Therefore, it pushes me up, right? And when the other person goes to the ground, he pushes his feet, right? And he then goes the other way, right? So at each time when you apply a short impulse, right, you change the movement. Okay, so there is a continuous change of application of moment torque. Okay, which is out of sync with each other. If they're acting together, then you can say it's a couple, right? But they're not acting together. In fact, they're acting at polar opposite times in a periodic motion. So that is a seesaw, right? Now, if they were both suspended like that in midair, right, with both the weights same, and you had a pivot in the middle, right? Now, what that would mean is that FD, F1 D1 will equal F2 d2. Okay, what does that, why is that, why is f1 d1 equal to f2 d2? Is because r cross f about the pivot. See, at the pivot there is a force, right? That force, when you take moments about the pivot, right, the mg and n there, right? So now see how, what are all the forces? First draw the free body diagram of the lever, right? There is mg, right? There is n, right? And if the pivot was slightly displaced, then one side will fall down, right? Because the n and the mg are not straightforward, right? So then you will it will introduce a second n, right, when it reaches the stop position, because the net um, r cross f's should all balance out, right? If it is like this, the forces balance out, right? So if I keep it like this, the mg is here and the n is here, right? But then it's still falling because there are two forces. Maybe they are in balance, but right, n equals mg may be true, but they are at a they are not at the same point. So there is a resultant couple which makes the whole thing spin. Okay. So now if these two were in balance, right, it takes a far smaller force on to hold to make see the sorry. So if you look at the force F2, right, F2 can be far smaller because the D is bigger. Okay. F2 times D2 will be the same as F1 times D1. So it takes a far bigger F1 to balance out a far smaller F2 because D1 is much smaller than D2. Okay, so you have to apply a bigger force to keep the whole thing in balance. Okay, so then so that is what causes the whole thing to stay balanced, right? Now you need another set of rules, which is the force equations, right? The force equations will readjust, right? And how are they readjusting? The normal reaction and the mg will not be exactly equal. They will in fact counteract the f1 and f2. Okay, so now let's look at the direction of the torque. Okay, our f1 d1 is this way, right? f2 d2 is that way, about the pivot. Okay, when you take moments about the pivot, normally when we say moments, we were talking about r cross f about that pivot. Okay, r cross f about the pivot will be towards me, r cross f about the pivot for f2 will be away from you, and therefore those two, this torque is this way, that torque is that way, and therefore the two torques will cancel. Okay, now this idea where you apply a smaller force to hold off a bigger force is called mechanical advantage. Mechanical advantage in lever terms is known as d2 by d1. So you use a smaller force to leverage a bigger force. Okay, so like when you dig or when you use this, what is that, sometimes you have this, you break a nut. I don't know if you've broken a walnut using one of those clippers, right? Walnut's very hard. So when you apply a force on this side, right, you're applying using the principle of a lever to produce a very strong torque on the walnut. When the walnut breaks, you use that, some kind of a pliers, right? Or how the pliers work. They are all lever based on the principle of the lever. Okay, F1 D1 equals F2 D2. R cross F is the torque. Okay, now the center of gravity is, we already discussed center of mass, right? Sigma um, integral r dm or sigma ri mi, right? we said that sigma ri mi will give you the divided by sigma mi gives you the position of the center of mass, right? Now, like that, there is this term called the center of gravity. Now, center of gravity is usually the same as the center of mass because gravity is uniform. But if you were not in a uniform gravitational field, right, then the center of gravity and the center of mass will not coincide. This is very rarely the case, that you will not be in a situation where center of gravity and center of mass don't coincide. Okay, so when they calculate the center of gravity, what they do is you can suspend it from three angles, suspend the body from three angles, and you draw a straight line through the body. From the point of suspension, you will get the intersection point of those three lines will give you the center of gravity. All the lines will flow through the center of gravity. Okay. Now, here is the the lever again. Okay, the simple example of the lever. Okay, so now here there's a lever which has a weight. Okay, it has about the point G. It has the whole length of the whole. It has two holds. What is that? Two supports, K1 and K2. At each point, it will get an R1 and an R2. Right? Its weight is 4 kilograms, and that is about the center. Right? And now there is another force P, which is which is also applied. Okay, so now he is asking what is the value of each of these terms. Okay, what is R1, what is R2? Okay, now R1, so think of it this way: there is a boy sitting here at this point P, whose weight is W1. Okay, then the mass of this rod itself is 4g. It is here. Okay, so now W1 is, he is giving, W1 is the boy sitting in the middle, his weight is 6g, 6 kilograms. Okay, so 6 times g, the weight of the rod itself is 4 times g. Now that is balanced by the two normal forces R1 and R2. Okay, so now you have only two unknowns and you have one equation. Now you have to use a second equation using torque. Okay, so now what he is going to do is he is going to take moments about some point. Okay, and if he takes moments about the center of gravity, about this point, right? If he takes moments about this point, then the uh, the um, the gravities, the weights, torque will be 0. Okay, so the torque due to K1 will be R1 times GK1 K1G, right? Negative R1 times K1G, right? Plus R2 times K2G plus uh, W1 times PG. Okay, negative R1 times K1G plus R2 times K2G plus W1 times PG when you take moments about G. About G. Okay, when you take moments about G, you take this one times that, this one times that, plus this one times that. Okay, so W1 times PG plus and R1 times KG, those two will be this way. W1 times PG will be R cross F towards me. For R2, it is again towards me. But for the other one, K1G, right, it is like this, and like this, it is into the paper. Okay, so it will be like this and into like this. Therefore, R1 times K1G will be into the paper. That will be negative. So the net sum of the three will give you a second equation. So R1 plus R2 equals 10G. R1 minus R2 equals 1.2 G. And therefore you solve for R1 and R2. Okay, so this is a simple example. The more common problem is one of these ladder problems, or several other problems that you will see if you took a class in engineering mechanics, which they make a lot of students take, particularly if you want to become a mechanical engineer or you want to become a civil engineer. Okay, so here is a ladder. The ladder problem is a very common problem, and you could be very well asked about the ladder problem. There is a ladder which is kept against a wall. Okay, just the ladder is kept against a wall. What is keeping it from falling? Okay, what are all the forces acting on it? Okay, see, the most important idea you must realize is that in the horizontal direction, right, at this point, he's saying that this surface is smooth. This surface is smooth. Okay, so if this surface is smooth, there is a normal force, right? Now, if the bottom surface is also smooth, right, then there is no friction. Okay, then the forces in the horizontal direction will not add up. Okay, if both surfaces are smooth, there is a force in this direction, the normal force like that, which is not counteracted. Therefore, as a result, the ladder will fall. Okay, and the ladder will fall down. Okay, so because there is a net force on it. Okay, but if there is friction, what does the friction do? As you know, static friction up to a point will be able to counteract whatever force is being applied on it, right? So if it is about to slip this way, right? So if it is about to slip this way, because normal force is that way, so it's going to slip this way. Therefore, static friction will push that way. So if the bottom floor is rough, the friction will be pushing this way. Okay, so n is like this, but because there is a net n2, right, that is going to push it that way. Okay, therefore the friction will be this way, counteracting that n2. Okay, so in the horizontal direction, when you do think of just forces fx, f will equal n2. Okay, in the vertical direction, the n1 force will equal mg. Okay, so now you have two unknowns, n1 and n2, right? How do you and f, as you know, static friction is it's not mu s times n. It is proportionate to whatever n2 is. It is also an unknown. Okay, so you have f equals n2. Both f and n2 are unknowns, right? N1 is mg, so now you know at least N1, right? So now, how do you evaluate both F and N2 if both are unknown, right? So for that, you use torque. Okay, what is the torque? So now he is saying, let us evaluate moments about B. Do you know why he's doing moments about B? It is because he can then kill two birds with one stone. Okay, you always take moments about one point which has multiple forces about that point, because the R in that case will become 0. Okay, so in this case, the R cross F for both N1 and friction about the point B will become 0 for when you take moments about the point B. Okay. Now, what can you say about mg? It is mg times mg times r, where r is bc sine theta, right? Now, that is the same as mg times L2 cos theta. L by 2 cos theta. What is L? L is the length of the rod, length of the ladder. Okay. So L by 2, mg times L by 2 cos theta, right? And n is like that, right? So now it is making an angle theta. Therefore, this is the angle between r and mg will be this, right? Therefore, sine theta, sine of that angle is same as the cos of this angle. Okay, so that's how he says L mg times L by 2 cos theta is actually mg times L by 2 sine of this angle, because that is r and this is mg. So r cross mg. Okay, so r is L by 2 mg sine theta, and sine of this angle is same as cos of this angle. Therefore, he writes it as mg times L by 2 cos theta. Okay. And in this case, what is r? For n, what is r? R is this. Okay. R is the full ladder. L. L times n2 times this angle. R cross f. Okay. That is, and this angle is again theta. If this angle is theta, this angle is theta. Therefore, r cross n2. Right? That is n2 times L times sine theta. From this, you can get a value for n, the n2. The aim of this second equation is to get the value of n2, right? So we said that f is equal to n2, but we don't know either f or n2, right? So now you know both f and now you know f and now you know n2. Because you know n2, you also know f. So now, what is the net force at this point? That is just square root of n1 square plus f square. Okay. Reaction at the bottom, including friction, you can then calculate. Now you calculated all the forces. Okay. So now the point of the ladder problem is you take moments. Okay. So in the case of rotational equilibrium, in the case of translational equilibrium, you have sigma fi equals 0, right? In the case of rotational equilibrium, you solve problems by taking tau external equals 0. So when we say moment, we're talking about moments of forces, right? R cross F, right? Moment of the force is torque. That's what they mean by moment. Okay. So now this is another ladder problem using moments. In the figure, a ladder of mass m is shown leaning against a wall. It is in static equilibrium, making an angle theta. It is exactly the same as the ladder problem we looked at before, right? The coefficient of friction, though, between the wall and the ladder is mu1. The coefficient of friction between the floor and the ladder is mu2. So now here the wall was smooth. Now the wall is also rough, right? The wall is also rough. So the normal reaction of the wall on the ladder is N1, that of the floor is N2. If the ladder is about to slip, then what is true? Okay. So if you take forces in the horizontal direction, N1 plus mu times N2 is just about to slip, right? So notice the wording, right? See, in the previous case, it was not slipping, right? So now, because he has two frictions, right, he is having an added unknown, right? There is a F here and there is an F there, right? But now he's saying that it is just about to slip. Okay, so if it is just about to slip, mu n comes into play, right? If it is just about to slip, the friction is mu n. Okay, that's the point he's making. N1 plus mu times N2, that is the force equation in the vertical direction, right? Vertical direction, N1 plus mu times N2. This mu times N2 is like that, right? So N1 plus mu times N2 equals mg. Then mu times N1 is this way equals N2, right? And then finally the torque equation, right? You will get only one torque equation here, so you get this torque equation mg times L cos theta, same as in the previous case. Takes moment about B, mg times L cos theta minus N2 times L sine theta minus, now you also have this friction, u times N2, right, times L cos theta, right? So when you plug that in, you end up with another equation, which then, and when you plug those numbers in, you will end up with N1 tan theta equals mg by 2. Okay, mu1 equals 0, mu2 equals not equal to 0, and n1 tan theta equals mg by 2. So that is the net result that he gets from this ladder problem. Okay, so the ladder problem is is you may get questions around moments, so you must know how to use moments a little bit. Okay, so now we already discussed this idea of motion of center of mass, right? So we did sigma mi ri divided by sigma mi gives you the center of mass, and if the center of mass is moving, it continues to move if there is no external force. If you differentiate second time, you end up with Newton's second law, F equals ma, right? So now, just as we introduce this idea center of mass, right, now we are going to introduce this idea called moment of inertia. Moment of center of mass is integral r dm, right? Moment of inertia, on the other hand, think of it this way, right? It is half sigma mi vi square, right? So when something is rotating, right, what is happening? What is the kinetic energy? It is the kinetic energy of every particle in that movement, right? And if everything is moving with a velocity v, right, then its net kinetic energy is half sigma mr square omega square, right? Now that sigma mr square, right, is the moment of inertia. Half I omega square, right? So it is, you can think of it in those terms, or you can think of it as the second moment, the moment of the center of mass. Okay, r square dm. R dm is the center of mass. Moment of center of mass is another r. So r square dm, integral r square dm, will give you the moment of inertia. Okay, so moment of inertia is sigma mi r square or r square dm, right? And this quantity is, it is the equivalent of, you can think of it as a rotational form of inertia, or rotational form of mass. It is the analogous to mass in linear dynamics. It has dimensions ml square. Okay, and it's usually denoted by the symbol I. I is sigma mi square. Okay, and there are a lot of rules around moment of inertia, and they will definitely ask you questions around moment of inertia. Okay. The moment of inertia does not depend on the angular velocity of the body. Rather, it is a property that is related to the mass as well as the shape and size of the body, right? Now, I'm sure you all watched these the Olympics is going on, right? In the Winter Olympics, there are all these ice skaters, right? An ice skater will start spinning with their hands open, then they will move their hands towards themselves, and then they will start spinning even faster. Okay. Now, why does that happen? That happens because of the conservation of angular momentum. Okay. When they stretch their hands out, I omega is angular momentum. Okay. I omega is conserved, right? You cannot do anything but change your own shape. Okay. Now, when you change your own shape, right, by bringing your hands together closer, right, your moment of inertia declines. Your angular momentum remains the same, but your moment of inertia declines. There is conservation of angular momentum, but your moment of inertia changes. Because your moment of inertia declines, I omega 1 equals I omega 2, I2, right? I1 omega 1 equals I2 omega 2, I2 is smaller than I1, and therefore omega 1 is less than omega 2. You start spinning faster because as you pull your hands together, your moment of inertia declines. Therefore, you start to spin even faster. So that is the idea behind the ice skater who starts spinning faster. So now it is basically it is a measure of moment of inertia is a measure of inertia in the context of rotational motion. We say that when we say that angular momentum is conserved when there is no external torque, we are saying that I omega is conserved. Okay, and so it takes, if you had a rod, right? If you had a rod, right, like this, and you made it spin like this, right, it takes a lot more to make it spin like this than if you had a rod and you wanted it to spin like about a midpoint axis. To make it spin like this versus to make it spin like this is different. Okay, it takes a lot more torque to make it spin like this than to make it spin like this, or more specifically, the angular moment of this spinning like this versus this spinning like this is very different. Okay, so remember that. Okay, now and so there are a lot of properties, etc., which deal with the moment of inertia. Okay, so now we will learn some of the ideas around moment of inertia of each of these devices, right? Now, the moment of inertia of a thin circular ring, right? Now, r square is about an axis, right? R square dm is about an axis, right? So now the moment of inertia, if there is a thin circular ring and you had a vertical axis and it was a thin ring like that, then all the dms are at an exact constant distance of r. Therefore, they will all have the r square. The r squares will be constant. You can pull the r square out. The sigma mi will become just m. So the moment of inertia of a thin circular ring is simply mr square if m is the mass of the ring and r is the radius, right, of the circle. So it is mr square. Now, here he has three particles in a triangle, and he does m1, and he looks at the moment of inertia about this axis, right? So this point itself has no r. R is 0 for this point. Although there is a mass here, there is no R here. But these 2 points have an A by 2 and an A by 2. So this one has M times A by 2. This one also has M times A by 2. Therefore, you have or M times A by 2 square, M times A by 2 square. Therefore, you will end up with MA square by 4 times 2. Therefore, you have the MA square by 2, right? Now, you have a masses fixed at the end of a massless rod with axis passing through their center of mass. Both masses are equal, and length of the massless rod is L. Therefore, you have I equals ml square by 2 plus ml square by 2. So therefore ml square by 2. Okay. So this case, right? So this is this case. So it is rotating about this axis, right? So this is L by 2. This is L by 2, and each of these, if you say, is so something like that. Okay. So now he has each of the there are two masses here which are fixed at the end of a massless rod. So now you had one mass here and one mass here, and then the whole thing was spinning, right? So now this one has ml square by 2, this one has ml square by 2, right? Now, if you had a thin rod where each, with a uniform length, right, like this, right, and you want to make it spin, right? So you want to calculate the moment of inertia of this thin rod about this axis, right? You have each of these points with a small delta L, right? So L square delta L will give you the m is equal to L times rho, right? Rho times x square dx. Therefore, you do the integration of rho times x square dx is x cubed by 3. Therefore, that will become L cubed by 3. So ml square by 3 will be the moment of inertia of this one about this axis. About this axis, if you want to make it spin. Now, if you wanted to make it spin about this axis, it is in fact much less. It is ml square by 12, because you're integrating only from 0 to L by 2, and on this side it is twice that. So 0 to L by 2, therefore you will end up with ml square by 12. 0 to integral 0 to L by 2, L cubed by 3, right? And therefore that will become L square by 4, right? Therefore, you have m by 2 and m by 2, so times 2. So L square by 4. Therefore, that's how you end up with 3 times 4. And then the whole thing, you have this side and then you have that side. Therefore, you have twice that. Therefore, you have m by 2 times L square. Therefore, you have ml square by 12. So once you have ml square by 12, uniform rod spinning about the midpoint, right? So that is ml square by 12. Compare that with ml square by 3. There is actually a theorem called perpendicular axis theorem, which states that ml square by 12 is about the center of gravity. About the center of gravity, you have the lowest moment of inertia. Okay. Now, about another axis, which is, say, parallel to the center of gravity, it is merely the moment of inertia about the center of gravity, which is ml square by 12 plus r square times plus m times r square. Okay. So, and this, in this case, r is L by 2. So ml square by 12 plus ml square by 4 will give you ml square by 3. Okay, so remember the perpendicular axis theorem and this one. There is also the parallel axis theorem and the ml square by 12, and then you end up with ml square by 3, right? And you can use that also to solve some of these problems. Uniform circular disk with axis perpendicular to the plane of the disk and passing through the moment of inertia, right? So this one is mr square by 2. It is a disk, right? So this is a disk. Okay, this is like a disk, right? So now it has a mass m and a radius r, so it is mr square by 2. Okay, and that is done by looking at it using thin disks. Okay, now each of these disks, let me show you. This is worth learning because you may end up doing a lot of problems involving this. At a distance r, there is a thin disk whose radius, whose thickness is dr. Okay, so the radius of a thin circular, we already evaluated this one. If you remember this one, right? Thin circular ring is mr square, right? So now, so you have di is, what is the m here? It is 2 pi r times dr. That is the area. 2 pi r is the circle, the circumference of the circle, times the thickness is dr. If you open it up, it will become 2 pi r times dr, right? Times rho, right? So area times rho, mass per unit area is rho. Okay, so 2 pi r dr times rho times r square, because di is equal to r square dm. This whole term is dm. Okay, 2 pi r dr times rho is dm, r square dm, di is r square dm. You do the integral, I is equal to integral di. Therefore, then you end up with r square r cubed dr. It will give you r to the power of 4 by 4, right? R to the power of 4 by 4, 4, and the 2 will get cancelled. Therefore, you have m rho r to the power of 4 by 2, right? But pi r square rho is m. Therefore, you have m r square by 2. Learn how to solve these problems. All right. So then next one is the hollow cylinder. Hollow cylinder is merely mr square. It is just a sequence of rings, right? You can think of a hollow cylinder about this. It is all just a bunch of rings. It is the same as the sequence of rings. It's just a sequence of rings about that axis. Okay, so we will quickly visit now. We introduced this term called the radius of gyration. Okay, the radius of gyration is essentially, if I said I is equal to mk square, right? We end up with all these fractions, mr square by 2, ml square by 12, right? The radius of the gyration tells you I is always of the form n times ml square, right? So now, if I wrote the n times L square as k square, right, then you end up with the corresponding k is said to be the radius of gyration. Okay, so now different, it looks different, therefore it has a different moment of inertia, but you kind of make it seem as though it is a constant mr square. So you have this mk square. Okay, so k is said to be the radius of gyration, the square root of n times L, where L is what, where n is, what is n? N is 3 by 5 for a solid sphere, 1 by 2 for hollow cylinder, 1 by 2 for this one. Okay, 1 by 2 for a uniform disk, and 1 by 12 for a uniform rod. Okay, so so now we will also introduce this idea called the perpendicular axis theorem and the parallel axis theorem. Okay, the parallel axis theorems will tell you that if it is a z about one axis, parallel axis theorem, Iz equals ICM, where Cm is about the center of mass, plus ma square, right? We already discussed that the moment of inertia about the center of mass is the lowest, right? Therefore, ICM plus ma square, if you have it about this is a by L by 2, right? So ml square by 12 plus ml square by 4. Therefore, you end up with ml square by 3. So that is the parallel axis theorem. Iz prime equals ICM plus ma square, where a is the distance between C and Z. Okay, so if you had to get the moment of inertia about of a uniform disk, you rotated the disk like this. Okay, rotated the disk like that. Okay, then you will have mr square by 2 about the center of mass plus the m times r square. Okay, so mr square by 2 plus m times r square will give you 3 by 2 mr square about the point on the, about an axis like this. Okay, so now perpendicular axis theorem, Iz, right, What it tells you is, if you wanted to rotate this one like this, I'm afraid to rotate it like this because this thing will fall, right? If you wanted to rotate it like this, what do? Right? So we know about this axis, we know, right? What it tells you is iy plus ix plus iy will equal iz. Okay. Now iz we already found, right? Now ix plus ix and iy are actually equal in this case, right? Symmetry, right? Therefore iz by 2ix equals iz. Iz we already calculated using integration. Therefore, ix equals iz by 2. Right? Iz we already said is mr square in the case of the uniform disk. Right? So this is called the perpendicular axis theorem. We already discussed the parallel axis theorem. So now you could have questions like this one: the moment of inertia of a uniform cylinder of length and radius r about its perpendicular bisector is I. What is the ratio I by r such that the moment of inertia is minimum? Okay, so anytime they say something is a minimum, it means you have to differentiate. Okay, so di, the moment of inertia of uniform cylinder of length and radius r, is about its perpendicular bisector is ml square by 12 plus r square by 4. Right? Now the volume is pi r square L. Right? So now if we assume that the volume is constant, right? So now basically he has a uniform cylinder, right? Now he is calculating the ratio of I by L by R. Okay, so now you have a cylinder, right? Now you can make it a thick cylinder, which is shorter, or a thin cylinder, which is longer, right? At what point is the moment of inertia minimum? Okay, now V is equal to pi r square L, right? That is the volume of a cylinder. Now the moment of inertia m times L square by 12 plus r square by 4, right? A moment of inertia about its perpendicular bisector is L, right? Um, is I, right? So now, so I is equal to m times L square by 12 plus um, um, r square by 4, right? And therefore, he then writes V equals pi r square times L, right? Therefore, he plugs that back in, okay, and into this equation for this L, he is going to substitute V by pi r square. Okay. Now V by pi r square for L, when you differentiate you and then you plug it back into the formula, you will end up with the answer. So di by dl, set di by dl equals 0. Okay. So you will end up with a corresponding result for L. Okay. So for r square is doing V by pi L. Okay. So when you differentiate these two terms, you will end up with a solution for this one. All right. So I'm going to stop here for today. We've kind of gone a lot of time over. So I will see you again next class. All right. So best wishes and happy study. All right.